see the problems. Those are asked in the crystal structure and then phase diagrams. Problem number 13. So this is assertion and reasoning. The statement 1 is metals have same crystal structure. Metals having the same crystal structure will have the greater solubility. That is the statement. And for that statement, we need to see the statement 2 and whether the statement 2 is justifying the statement 1. So why the statement, what is the statement is saying? The metals having the same crystal structure. What is the meaning of same crystal structure? For example, if I have a crystal structure something like a FCC, if I have a metal something like a ferrous which is having FCC structure, and if I am mixing another metal, let's say carbon or some other metal, and the carbon structure also should be FCC. That is the meaning of this. This is just an example, so don't think that don't literally take these. C is FCC and Fe is SCC. For example, Fe is SCC and I need to add the gold. Okay, if I add the gold which is having the FCC structure, then the solubility of the gold within the ferrous is very high. That is what this statement is saying. Why is that? Because the difference in the crystal structure limit the solubility. Why? If there is a difference in the crystal structure, for example, the Fe is FCC and you are trying to mix BCC structure, then the solubility, there is a limit in the solubility. Okay, so this statement also explaining the first statement, so that the option is A. Okay, both are true, and the statement 2 is explaining the statement 1. Okay, what is the statement 1? They are saying that crystal having the same, metals having the same crystal structure are having the greater solubility. Why? If they don't have, then it limit the solubility. So here we have seen like Hume rotary conditions. So there are two types of solids, substitutional and interstitial solutions. So in the substitutional, these are the conditions those should be followed. What is that? Crystal structure. First of all, the crystal structure of each element of solid solution might be same, so that there will not be any different phases. If both are having the different phases, different structures, still they are able to mix with each other, but they will produce some phases, different phases. Okay, so if there is no phase, then we can say that the solubility is very high. They both look like same. And the size of atoms of each elements, how you define the size of the atom? It is based on the radius of the atom. So they must not differ more than 15% the size. Okay, and they should have electronegativity is very less. Okay, less means the difference in the electronegativity. Otherwise, what happens if they have more electronegativity? Then what happens? They will attract each other, and then they form the chemical compound. Okay, so they should not form any chemical compound here. Okay, and another one is element should have the same balance. Okay, otherwise how can you satisfy the neutrality? So these four conditions should be satisfied here. And another question 48, which of the following features of atoms determine the degree to which the solute atoms dissolve in the solvent atoms? What is the solute? Okay, the element or whichever we are trying to dissolve into the another solution, that is called as the solute, and then whichever is taking that particular solute, then it is called as the solvent. Okay, so see, they are saying atomic size factor, which of these three will influence the solubility. So they are saying atomic size factor. What is the meaning of this? This is the difference between the size of the solute and the solvent. Okay, and then crystal structure. Okay, that means whether it is a FCC or BCC, like that. And the electronegativity, if they have electronegativity, more electronegativity between the solute and the solvent, then they will form the chemical bonding. So this is also affecting. That means all these three are affecting. This already we have seen in the question number 13 also. So 1, 2, 3. All these three are affecting the solubility here. So under question 14, this is related to the phase diagram. Statement 1, that tie line is constructed across the two phase region at a temperature of alloy. So what is the meaning of this? See here, we have seen this. For example, if I take the binary phase diagram here, this line from U to V which is drawn here is called as a tie line, and where it is drawn, see this is a liquidous line and this is a solidus line. Okay, so here liquid is slowly converting to the solid here, and from a solid here, between this is liquidus and solidus, we have a mixture of liquid and as well as the solid, and once if you crosses this curve, then everything is a solid here. Okay, so in between this liquidus and solidus, we have a mixture of a liquid plus a solid. So we want to know what is the composition at different positions of the element A and as well as the element B. Okay, to know that we need to draw a tie line. So by drawing this tie line, you can find the composition of this element A and as well as element B. So that is the purpose that we draw the tie line. Okay, and here if you observe here, the tie line is at a particular constant temperature. Why? Because whenever there is a phase change, the pressure and as well as the temperature are always constant until the phase change is completed. Okay, this is the meaning of this. So statement is saying that it is constructed across the two phase region at a temperature of an alloy. Alloy means here we have two elements A and B. Okay, the solid solution of two metals is called as the alloy. And why we are drawing this, why we are drawing, that should be explained in the statement 2, which is a reason. So why the overall alloy composition is located on the tie line, that is why we are drawing this. Okay, okay, so this is explaining the statement 1. So both are correct, and this is the correct reason for the statement 1. So we will go for the answer here. And apart from the tie line, we also come across sometimes the lever rule. So lever rule is nothing but the tie line, but here we will directly find the fractions or amount of A or B, but whereas in case of a tie line we will find out the composition like in terms of percentages. Okay, and for to understand this further, I will try to take some example here. See, let's say A is changing from 0 to the 100, and let's say the point V is giving the value at 70 for the A. Okay, and also at the U. What is the meaning of this? See, the tie line, for example, I have a composition of A, I have a composition of A at a point B. I have a composition of A at a point B. What is the meaning of that? For example, here liquid plus, here we have a liquid plus a solid, and we also have A plus B here. Okay, we have a element A plus element B, or metal A plus metal B. So here at this position, I know this element A or metal A is having the 50%, and remaining 50% is a B. Okay, so at this 50%, I want to find out what is the amount of liquid, liquid A and solid A. Solid A. Okay, so here at 50% I have A plus B. So here I have 50% of A, and remaining 50% is a B. Okay, at 50% of B, A, what is the liquid A and what is the solid A? That is what I want to find out. Okay, so I will approximate these values. Let's say the point V represent the solid state of the V. Why? Because this is a solidus line, and the point U represent the liquid state of the A, because it is on the liquidus line. Okay, so according to the home rotary or tie line method, what is that? For example, A liquid. If I want to find out the A liquid, then I need to take this portion which is nearer to the solid. Okay, so let's say that is a BV divided by total length of the tie line. What is the total length? That is a UV. Okay, so I will approximate V to the 70, okay, and U to the 30 for the sake of our convenient. So what is the BV? V is a 70, so let's say in terms of the percentages, this will become 0.7 minus B is a 0.5, that means 50 percentage, okay, divided by total is how much? 0.7 minus 0.3, okay, that means 0.2 divided by 0.4, so it will become a 50%, okay. That means at this position liquid percentage is 50%, so automatically a solid will become 1 minus 0.5, that means this is also 0.5 or 50 percentage, okay, this is a 50 percentage. Otherwise you can again find out as equal to, if you want to find out the solid, then you need to take liquid term, okay. Liquid term is UB divided by UV. B is 0.5 minus 0.3 divided by 0.7 minus 0.3, again 2 by 4, 0.4 by 0.2 by 0.4, again we will get the 50 percentage, okay. So here this is how we can find out the liquid and as well as a solid composition of the metal A at a given percentage, within the A plus B, at a given percentage within the A plus B, okay. That is how we need to find out. And next question is 51. So this is again a direct question. In which one of the following phase transformation there is no, underline the no compositional alternations. See, the composition is different from phase, okay. These two are different. They are saying phase can change, your phase can change, but its composition should not change. What is the meaning of this? For example, if I melt the ice, it will become the water, okay. The phase changed, but its composition never changed. What is the meaning of that? It is remain H2O only, okay. Its composition is not changed. But whereas here it's a composition, if a composition change, then it composition is not changing, then what is the name of that particular reaction? Though we have seen that is a that is a incongruent transformation, okay. Incongruent. If it is a congruent, then sorry, it is a congruent. It is a congruent, sorry, option is a B. So if there is a no change in the phase, then it is called as a congruent. If there is a change, then it is an incongruent, okay. So we have seen like what is the example for that? Allotropic transformation and melting of a pure substance. But in case of incongruent transformation, at least one phase will undergo a compositional change, okay. For example, all invariant reactions, melting point of isomorphous alloys. What is the invariant reactions? Invariant reactions are nothing but, for example, we have defined what is the invariant points, okay. What is the invariant points? For example, this is the invariant point. What is this? This is the eclectoid point. This is a iron carbon diagram, okay. In the iron carbon diagram, this is a eclectoid point and this is the eutectic point, okay. At this particular temperature and pressure, if I go up, then what happens? Alpha is a solid and Fe3C cementite is a solid. Two solids are becoming a liquid. And in the same way, if I come down, then what happens? One liquid is transforming into two different solids. Okay. So this is a invariant reaction, and this point is invariant point. The reaction that are happening at that position is called as that. And here one more point is there. What is that? Eclectoid point. Here what is happening? The composition in the liquid phase is different for the iron and carbon, but whereas when you decrease the temperature, then they are changing into the two different solids, and these two different solids are having two different structures. Okay, that means their composition is changing. Alpha iron, this is alpha gamma iron, and this is Fe3C. Okay, their composition structure, everything is changing. So that means here this is an incongruent reaction. Okay, but whereas in case of a congruent, there is a no change in the composition. Phase may change, liquid to solid, it is become liquid to solid. Phase may change, but the composition will not change. Okay. Start. So next question is 47. So the number of atoms per unit length whose centers lie in a directions vector for a specific crystallographic direction is called. This is the linear density. So this is again direct question. So linear density. Linear density is defined as a number of atoms centered. This word is important. Centered on a direction vector to the length of the direction vector. Okay, and here we will also see the planar density. What is the meaning of that? Number of atoms centered on the plane. This is on a vector and this is on a plane, and we will take the area of the plane. We divide with the plane. For example, here let's say this is a plane. On this plane, I have a atom like this, and I have one more atom like this. Okay, here if I take the the vector like this, I have taken the vector like this, and here the center of this particular atom is here, and this particular atom is here. Let's say this is a R and this is a R, and the distance between these two is let's say 2r. Okay, then here in this case, how you find out the linear density? LD equal to number of atoms centered on the direction. Number of atoms, here there are two atoms that those are centered, but here those full atoms are there on this line are only one fourth atoms are there, not full atoms are on this particular vector. Okay, so we need to divide with the 1 by 4th. Okay, divided by length, the length of the direction vector. See, I am taking this from this center to this center. What is the length of that? 2r plus r, that is a 4r. Okay, so it will become how much? 1 by 8r. This is how I need to find out. Okay, and for the same case, if I want to find out the planar density, so PD equal to number of atoms centered on the plane. See how many atoms? 1 and 2, but again how much portion is lying on this? Only one. one by 4th. Okay, and area of the plane. Okay, area of the plane. For example, if I assume this as a in something like a square which is having a the dimension as a and a, then it will become a square, and we can find out the relation between a and r, so that you can substitute based on the answer options given in the exam. Okay, next question 52. In a simple cubic structure, the atomic power factor is nearly power, or it is also called as a packing factor. Okay, how many atoms are packed in a given structure? Okay, this is again a direct question. So atomic packing factor or power factor is defined as the volume of the atoms in a unit cell divided by volume of the unit cell. I am not going to derive this, we have already seen this. Okay, please go back to our video lectures. But here again I would like to emphasize or recollect some of the important things related to this. See, for the simple cubic we have this coordination number. Okay, coordination number means what are the nearest to neighboring atoms for any atom that you consider. Okay, so for the simple cube it is a 6, and BCC body centered cubic it is a 8, and FCC it is a face centered cubic it is a 12, and hexagonal 12. Okay, for hexagonal and FCC more. And A by R, what is the R? R is the radius of the atom. We have considered each atom as the sphere shape. Okay, so here A is the edge of the cube. So A by R is here 4 by root 4, 4 by root 3, 4 by root 2. See here the numerator is constant, that value is 4, but only denominator is decreasing, that too in a proper way, root 4, root 3 and root 2. Okay, So it's very easy to remember like this. And here number of atoms, even though we have a so many neighboring atoms, how many atoms are there in this? See total number if you consider full volume. So here in case of simple cube 1 and BCC 2 and then FCC 4 and hexagonal 6, you need to remember this. Okay, so to derive this formula we need to remember all this coordination number, the relation between A by R and the number of atoms, then it is very easy to find out. Okay, and then finally APF. What is APF? Volume of the atoms. This is for the atom, volume of the atom, and volume of the unit cell. Volume of the unit cell is different from the atoms. Okay, for the volume of the atom, how you get, this is the spheres. Okay, how, based on the number of total atoms you will multiply this n into the volume of the sphere, that is the 4 by 3 pi r cube. Okay, and here what is the volume of the unit cell? That is the volume of the cube. Okay, that is in terms of the A. So you have R and A and you substitute this value so that you will get the finally these values. So for a simple cube it is a 0.52, and for a FCC and a hexagonal this is the 0.74. This is the highest maximum possible value, where you can you can pack those many densely atoms. Okay.